From the dawn of humanity we have gazed up at the heavens, our eyes filled with wonder and curiosity. The night sky, with its twinkling stars and vast expanse, has always been a source of inspiration and mystery. Ancient civilizations meticulously charted the stars, creating intricate maps that guided their understanding of the cosmos. We yearn to touch the sky, to soar like birds, free from the constraints of the earth. The graceful flight of birds captivated our imagination, symbolizing freedom and the boundless possibilities of the skies. Our ancestors wove myths about flying creatures, dreaming of impossible journeys through the air. These stories were more than just tales, they were expressions of our deepest desires to conquer the skies. Early inventors sketched designs of flight machines, laying the groundwork for future innovations. We defied gravity with balloons and gliders, pushing the boundaries of what seemed possible. The sight of hot air balloons floating gracefully in the sky and gliders soaring on air currents marked the beginning of our journey into the realm of flight. The invention of the airplane marked a turning point in human history. The Wright brothers' successful flight in 1903 was a monumental achievement, proving that controlled, powered flight was possible. This breakthrough opened the door to a new era of exploration and connectivity. It transformed our relationship with distance and time. Suddenly continents felt closer and the world seemed to shrink. Air travel revolutionized the way we connected with each other, making it possible to traverse vast distances in a matter of hours. But with each milestone in aviation, a new desire emerged: the need for speed. The quest for faster and more efficient aircraft became a driving force in aviation technology. Early propeller planes gave way to jet engines, shattering the sound barrier and ushering in a new age of high-speed flight. The development of jet engines revolutionized air travel, making it faster and more accessible. We celebrated Chuck Yeager and the Bell X-1, marvels of engineering that redefined what was achievable. Yeager's historic flight in 1947, breaking the sound barrier, was a testament to human ingenuity and determination. The pursuit of speed became a symbol of human ingenuity, a testament to our relentless spirit of innovation. Engineers and scientists worked tirelessly to push the boundaries of what was possible, achieving milestones that once seemed like science fiction. Today that pursuit continues in the realm of hypersonic flight. Modern engineers are developing aircraft that can travel at speeds exceeding Mach 5, pushing the limits of technology and human capability. This is a world where speed is measured not in miles per hour but in Mach numbers, multiples of the speed of sound. Hypersonic flight represents the cutting edge of aviation technology, promising to revolutionize travel and transportation. It's a world where aircraft pierce the sky at unimaginable velocities, leaving sonic booms in their wake. The future of flight holds endless possibilities as we continue to push the boundaries of what is possible, driven by our unyielding desire to explore and conquer the skies. The quest for hypersonic speed began in earnest in the 1950s. A time when the boundaries of aviation were being pushed to their limits. The world was captivated by the idea of breaking through the atmosphere and reaching the edge of space. Central to this quest was the X-15 experimental aircraft, a groundbreaking project that sought to explore the unknown realms of high-speed flight. This rocket-powered plane was a marvel of engineering for its time. It represented the pinnacle of aerospace technology, combining cutting-edge materials and innovative design to achieve unprecedented performance. The X-15 was designed to touch the edge of space, reaching altitudes where the sky turned black and the curvature of the Earth became visible. It was a bold vision that required overcoming numerous technical challenges, and touch it did, setting speed and altitude records that stood for decades. The X-15's achievements were a testament to human ingenuity and the relentless pursuit of progress. On October 3, 1967, William J. Knight piloted the X-15 to its record-breaking speed of Mach 6.7, or over 4,500 miles per hour. This was a momentous occasion in the history of aviation. This incredible feat demonstrated the raw power of rocket propulsion. The X-15's engines were capable of producing immense thrust, propelling the aircraft to speeds that were previously thought impossible. It showed that we could push beyond the limits of conventional jet engines. The X-15's success opened up new possibilities for high-speed travel and space exploration. But the X-15 was not without its limitations. Despite its impressive capabilities, the aircraft faced significant challenges that needed to be addressed. Its rocket engine, while powerful, was incredibly thirsty. The fuel consumption was a major concern, as it limited the duration of each flight. It guzzled fuel at an astonishing rate, requiring vast amounts of propellant to achieve its high speeds and altitudes. This meant that the X-15's flights were short, lasting only minutes. Each mission was a sprint, not a marathon, with the aircraft quickly reaching its peak performance before having to return to Earth. It was a sprint, not a marathon. The X-15's brief but intense flights provided valuable data and insights that would inform future aerospace projects. The X-15 taught us invaluable lessons about hypersonic flight. Each mission contributed to our understanding of high-speed aerodynamics, propulsion, and the effects of extreme conditions on both the aircraft and its pilot. It highlighted the challenges of heat management, the need for specialized materials, and the critical importance of fuel efficiency. Engineers had to develop new technologies to protect the aircraft from the intense heat generated during hypersonic flight. Most importantly, it paved the way for new generations of engineers to dream bigger, to imagine sustained hypersonic flight. The legacy of the X-15 lives on in today's efforts to develop aircraft that can travel faster and farther than ever before, pushing the boundaries of what is possible in aerospace technology. The limitations of rocket propulsion led to the exploration of new engine technologies, ramjets and scramjets. While rockets have been the backbone of space exploration, their reliance on carrying both fuel and oxidizer limits their efficiency and range. This has driven engineers and scientists to innovate and develop alternative propulsion systems that can overcome these constraints. Unlike traditional jet engines that carry their own oxygen, ramjets and scramjets scoop air from the atmosphere. This fundamental difference allows them to be lighter and more efficient, as they don't need to carry the extra weight of oxidizers. By utilizing the surrounding air, these engines can achieve higher speeds and greater fuel efficiency. This air is compressed and mixed with fuel, creating thrust. The process begins with the air being drawn into the engine at high speeds, where it is then compressed to increase its pressure and temperature. Fuel is injected into this compressed air, and the mixture is ignited, producing a powerful thrust that propels the aircraft forward. Ramjets work efficiently at supersonic speeds, several times faster than the speed of sound. They are designed to operate optimally in the range of Mach 2 to Mach 6, making them ideal for high-speed aircraft and missiles. The simplicity of their design, with no moving parts, makes them robust and reliable for sustained supersonic flight. However, they have an upper speed limit. Beyond Mach 6, the efficiency of ramjets decreases, and they struggle to manage the extreme temperatures and pressures encountered at higher speeds. This limitation has led to the development of scramjets, which can operate at even higher velocities. Scramjets, on the other hand, are designed to operate at hypersonic speeds, exceeding Mach 5. Unlike ramjets, scramjets maintain supersonic airflow throughout the engine, allowing them to function efficiently at speeds up to Mach 15 and beyond. This capability opens up new possibilities for rapid global travel and advanced military applications. The key to a scramjet's performance lies in its ability to manage the incredibly high temperatures and pressures generated at hypersonic speeds. The materials used in scramjet construction must withstand temperatures exceeding 2000 degrees Celsius, and pressures that can crush conventional materials. Advanced cooling systems and heat-resistant materials are essential to ensure the engine's integrity and performance. This requires advanced materials and innovative engineering solutions. Engineers are constantly pushing the boundaries of material science, developing composites and alloys that can endure the harsh conditions of hypersonic flight. These innovations not only enhance the performance of scramjets, but also contribute to advancements in other aerospace technologies. Imagine a furnace blasting air at thousands of miles per hour, and you begin to grasp the challenges. The extreme airflow and temperatures create a hostile environment that tests the limits of engineering and material science. Overcoming these challenges is crucial for the successful development and deployment of scramjet technology. The development of scramjet technology has been a long and arduous journey. It began with theoretical studies and small-scale experiments, gradually progressing to full-scale testing and prototype development. Each milestone has brought new insights and challenges, requiring continuous innovation and perseverance. It has involved countless hours of research, testing, and refinement. Teams of scientists and engineers have dedicated their careers to advancing scramjet technology, conducting experiments in wind tunnels, and analyzing data to improve engine performance. Their collective efforts have paved the way for the next generation of high-speed propulsion systems. But the potential rewards are enormous. Scramjets offer the promise of revolutionizing air travel, enabling flights from one side of the globe to the other in just a few hours. They also hold the potential for rapid response military applications, providing a strategic advantage in defense and security. Scramjets offer the promise of sustained hypersonic flight, opening up a new era of high-speed travel and military applications. The future of aviation and aerospace is poised for a transformation, with scramjets at the forefront of this exciting frontier. As research and development continue, we can expect to see even more groundbreaking advancements in the years to come.